I don't know if you guys can hear that, but all of a sudden, something's happening right outside my door. And this is
Oh, I only hear your voice, so I think you're okay.
You can hear my voice, you say?
Yeah, I can hear your voice fine. I don't hear any other noise, so I think you're
Okay.
okay.
I'm gonna actually get my earbuds because that's gonna help me.
Okay.
I can't believe it. The very minute. Okay, now I need to check my audio again. Can you hear me?
Yes.
Can you hear? You can?
Mm-hmm.
Okay. And so I've got that and that and okay, I think
It all looks good on this end.
Pardon me?
It all looks good on this end.
Okay, so can't believe this has happened. All right, so I'm not going to be checking the chat. So if anything comes up that needs to be addressed right away, please feel free to unmute and say something and interrupt. So the title of my talk is Building a Model of Zebrafish Epiboly using TissueForge, a particle-based simulation framework, a progress report. And if you haven't heard of TissueForge, but you've heard of Mechanica, they're one and the same. Mechanica has had a name change to TissueForge, and it has recently been publicly released, so it's available for anybody who would like to try it out to do so. So my project is part of Core Thrust C1 on developing simulation tools, and it's related to projects 3A1 and 3A2 on the mechanisms of zebrafish epiboly. So my background is sorry, I'm really distracted by the noise. My background is in laboratory embryology research more than modeling. So this will be from the perspective of an experimentalist trying to cross over and become a modeler. So this will be, yeah, I'm sorry. I'm sorry, I'm really distracted. I am gonna take this into another room and see if that helps me out, because this is the worst thing that has ever happened here. Okay. I was saying that right now I'm trying to become a modeler. I'm in the middle of actually learning how to leverage TissueForge to build tissues and build a model embryo suitable for investigating epiboly. And so this is going to be a progress report on those efforts, and it'll be more about the tool than about the embryo itself. So I will give you a brief outline of epiboly from the point of view of modeling it. Then I will tell you about TissueForge and its building blocks and features. Then I'll describe what a computational model of epiboly might look like in TissueForge, and then I will describe my journey so far and what I have to show for it. So the first step in modeling is to take stock of your structural components. So what are the things in your model? And so the zebrafish embryo at the start of epiboly consists of one large yolk cell, and on top of that is a layer of small mesenchymal cells called the deep cells. On top of that is a very thin squamous epithelial layer called the enveloping layer, or EVL. And we can also consider a fourth layer, the yolk syncytial layer, which is a layer of syncytial nuclei inside the yolk cell itself, underlying the deep cells. Next is to look at what are the cell and tissue movements that we would like to describe. And the main movement of Epiboly is coordinated spreading and thinning of all of these layers together, stretching out towards the vegetal pole until the yolk is engulfed completely. And this involves tissue deformation, cell shape change, cell rearrangement, and just to keep in the back of our minds, gastrulation is happening at the same time. So there is a bulk movement of cells from ventral towards dorsal, and the creation of the germ layers and the axial structures on the dorsal side. And these processes are very likely intertwined. So finally, we'd like to be able to test candidate mechanisms underlying those movements. So some factors that we believe to be important include, first, a pulling of the margin of the yolk syncytial layer and also the EVL towards the vegetal pole along arrays of microtubules inside the yolk cell. And there's also constriction, circumferential constriction of an actin ring around the margin. And that's actually two rings of actin, one in the EVL and one in the cortex of the yolk cell. Cell adhesion is also playing a role, both in the deep cells, where the cells adhere to the underside of the EVL and probably get pulled along passively. And also in the EVL, where the marginal EVL cells are tightly anchored to the surface of the yolk cell. And of course, we're also interested in regulatory mechanisms that control all of these processes. Okay, so what is TissueForge? It's a particle-based simulation framework emphasizing cell and tissue level modeling. It's an open source framework, so community contributions are encouraged. It's a C++ library with a Python interface, so you can simply import it into a Python script or a C or C++ program. And it's compatible with your favorite development environment, including Jupyter notebooks. So the challenge is, well, actually, no, I almost skipped a slide verbally. Here we are in TissueForge, basic building blocks. TissueForge is a molecular dynamics approach to modeling. So the basic building block is the particle. And particles are point masses rendered as spheres. And particles exert forces on one another, both attractive and repulsive. And these are described by energy potential functions, which give you the energy as a function of the distance between the particles. And the framework also can handle chemical species, so fluids, chemical diffusion, decay, secretion, and uptake based on SBML. And particles can represent objects at any of a range of different scales, but since the point here is to facilitate modeling at the biological level, I was going to say scales from atomic all the way up to like macroscopic, but since we're focused on the biological scale, we have a couple of properties that are based on the interpretation of particles as being cells or something roughly at the level, the scale of cells. And so, for example, we have particle splitting, where one particle can become two, which is like a simple mitosis that you can customize. And also particles are categorized into distinct particle types in the same way that cells are categorized into distinct cell types. And a particle can change its type, so you have something like cell differentiation. Finally, there's some features that are not yet in the platform, but are on their way. One is antimony, which is a language for describing differential equations, the rate equations for chemical reactions, and it'll be spatialized so that it'll be like on a cell by cell or particle by particle basis. And we'll also be able to use vertex models to describe arbitrary shapes of objects so that they're not just spheres. Okay, so the challenge is how to use those basic building blocks to build a model that's able to capture the complex structures and movements and mechanisms of a multicellular system. So when Brent asked me to give this talk, he said, I think folks will be interested in the why, when, and how to use tissue forge or this kind of approach to simulate your own models or to your own systems. But I'm not going to be talking about the why or the when today, because actually that's what I'd like to know. I mentioned that I'm new at this and just sort of parachuting in. And so I'm hoping to learn by doing, like what are the pros and cons of different modeling approaches. So right now I'm focused on the how. So that's what I'll be sharing with you. So it would be nice in the long run to have a complete model that incorporates all of the things the components that I mentioned. So all the layers, all the forces, representing all the cell and tissue shape changes and candidate regulatory pathways, et cetera, et cetera. But I will start simple instead and build a very stripped down, almost cartoonish version as a starting point. And so here is what I'm attempting to do. First of all, I will just consider two layers, the EVL and everything else. And my everything else will be a single particle. Furthermore, my EVL will be composed of spherical cells, not the thin squamous cells as in a real EVL. And that's partially for practical reasons, because that's what I'm able to do in Tissue Forge today. But also it may turn out to be sufficient. So I think time will tell whether having the right cell shape is important for capturing the dynamics of all this or not. So we'll see. Then, in order to make sure that they're not just a loose collection of cells, but actually an epithelium, I will have a spring-like potential interactions between neighboring particles to represent the mechanical coupling of epithelial cells. To represent something like the forces along the microtubules, I can add an external force acting on the marginal cells of the EVL. And likewise, to represent the circumferential actomyosin contraction, I can add circumferential forces that will constrict that leading edge. Okay, so now I'll take you on a little tour of my stepwise experimentations in model building. So it starts off simply enough. With a few lines of Python, I can define some particle types and create some particles. So over here on the left, I'm defining 3 particle types with some basic properties. And you can see I've given them very non-biological names, and that's for psychological reasons, to remind myself not to take them for granted, and that Tissue Forge doesn't impose any cellular or any particular biological meaning or character on your particles. That's up to you. So they will only be as biological as I make them by virtue of the properties that I give them. And you'll see a little more what I mean by that as we proceed. So anyway, those are my types, and little is going to represent the EVL particles, and big is going to represent my one yolk plus everything else particle. And I have a third type called leading edge, which is going to represent my marginal EVL particles. And by the way, this illustrates that particle types don't necessarily have to be identical with what we would think of as cell types. I don't think anybody would say that the marginal EVL cell is a different cell type than the other interior EVL cells, but they are in a different physiological state, and they experience different environment, different forces, different chemistry. And so you can use particle type when, for whatever reason, you want to distinguish between two sets of particles that you handle differently in the simulation. Okay, so now I've got my types, and so I'll now create some particles. In the upper right here, I'm creating one single big particle and specifying its location in the center of my simulation universe. And then beneath that, this line is creating a whole bunch of little particles all at once. And the parameter that I'm passing is actually a list of coordinates for where to put them. But now the harder part is figuring out where exactly to put them. So what are those positions? So this is part of getting to your initial conditions, getting to the point where you have set up an embryo and can say, okay, now I have an embryo, what happens next? So a lot of what I'm going to show you is about getting to the initial positions, and that may seem kind of dry, but it'll actually give some really important context for understanding how this all works and what happens after that. So here's a bunch of particles, and I think you can tell which ones are which. And just focusing in on the blue ones, I used a function that generates a list of random coordinates on the surface of a sphere. And but you can see that they're not very uniformly distributed, and that's okay. There's actually a wide range of ways, any number of ways to generate some points and use them for the first position of your particles. And I tried out a bunch of them. And in the end, none of them are going to give you like a natural distribution of particles that actually matches what you see in an embryo. And so what you do instead is you use whatever method happens to be convenient, and then you rely on an equilibration step by which you set the simulation in motion, and the cells start to move, and they sort themselves out and get into a configuration where you want them. So what do I mean by that? This is where the potential functions that I said come into play, and they are what give your particles substance. They are what make them behave like objects instead of just geometric shapes. So you can see here, a lot of these spheres are overlapping, and that is something that geometric shapes can do, but not something that objects can do. Two objects can't exist in the same place, and so I'm going to use a repulsive force to allow them to exclude each other from each other's volume and push each other apart and take up a more natural configuration. So here in the code, in the second line here, I am creating a Python object, and that object represents a potential function, and it represents the repulsion between two small particles. And then taking that object and associating it or binding it with two particle types. And in this case, they're both the same particle type because this represents how one particle of that type will interact with another particle of the same type. And in this case, I'm using one of the simplest potential functions provided by TissueForge. It's called the harmonic function, which is basically just a spring. And this is the spring constant, K. TissueForge provides a whole bunch of different functions that you can use, and you can also customize and create your own if you need to. As I said, it's repulsion because I'm allowing the particles to push each other apart. And if they're too close, they'll push each other apart until they're not. So what do I mean by too close? As everything with TissueForge, that's up to you. So I'm defining it by the radius of the particle, so that too close means they overlap, and if they they'll push apart until they no longer overlap. So over here on the right is an example of a potential function, and it's showing energy on the vertical axis as a function of the distance between the particle centers, or r, on the horizontal axis. And this is not actually a harmonic function. This is one of the other ones. I just happen to have that figure handy. But it does share one very important feature with the harmonic function, and actually with most of the functions that are available in TissueForge, and that is this concept of R naught, or equilibrium distance. So R naught is that distance at which the energy of the function is at a minimum. And so if you think in terms of systems moving towards their lowest energy state, that would be this. And so that's why it's the equilibrium distance, because the particles end up at that distance from each other. Or if you want to describe it in terms of forces, R naught is that distance at which all repulsive and attractive forces are balanced. And so the net force on the particle is 0. And so they don't move relative to one another. And so if you have two particles that are closer than that, so over this part of the graph, then repulsive forces dominate and they'll push apart until they get to that distance. And if your particles are further apart, then attractive forces dominate and they'll move together until they reach that distance. That is assuming that you have the attractive component of the potential implemented. Here I'm using just a repulsive component. So, okay, so now let's see what happens when we have that. So here's that initial setup, and I'm going to set the simulation in motion, and what that means is that the clock starts. And in each time step, the system calculates all the potentials. From that, figures out what are all the forces on all the particles, and from that can assign a new velocity to each particle, and from that can update the particle's position, and do that for all the particles and repeat each time step. So do that, set that going, and just as advertised, the particles now push each other apart until they no longer overlap and equilibrate into a much more reasonable configuration that is more like an embryo. Now, I should point out here that the one potential that I showed you in between the small particles and each other is not the only potential that I use. If I did, these particles would go all over the place. There's nothing special, for example, about this big red circle, which is just a geometric shape until I give it some properties that make it into an object. So I have also potential between the small particle type and the large particle type. And in that case, I have both attractive and repulsive forces. So that repulsive for the same reason described, so that they can't overlap, otherwise the particles would go inside the red cell. And likewise attractive, so that they'll stay on the surface of the sphere, otherwise they could just get pushed off into space there. So they're constrained to the surface of the sphere, and within that constraint, the repulsion between the small particles lets them spread out, as you saw. So now that I have something that looks like an embryo, what happens then if we try to simulate the microtubule pulling and add forces to pull the cells down toward the vegetal pole, and they're going to act only on the yellow particles, just as in the embryo, the microtubules are only interacting with the marginal cells. So I set that in motion, and it's not very interesting at all. And the reason is because, as I mentioned, for the purposes of equilibration, there's only repulsive force, no attractive force between these particles. Now, in the generic case of biology in general, cells don't generally attract each other, at least not in the mechanical sense of attraction. And so I think that generally you wouldn't want to use an attractive force, but in the case of an epithelium, an attractive force can represent the fact that the particles are, or rather the cells are attached to each other, so that if you were to pull them apart, they would resist that that stretch, and they would want to hang on, want to pull back together. Or if you just pulled one of them, the other one would be dragged with it. So without an attractive force, there's no attachment. Without attachment, you don't have an epithelium yet. So I'm going to add attractive forces. So here's what happened the first time I tried adding attractive forces. So at this point, the equilibration is finished. Up until this point, I had only repulsive forces. Then I added attractive forces between among the small particle type. And so here's what happened. It was not at all what I expected. Quite a surprise and quite an unpleasant one. The particles are all clumping together and kind of beating up like little drops of liquid. And it was quite horrifying. But the reason that this happens, apparently, is that you have a particle that's attracting a nearby particle, but it's also attracting particles that are further away. And this sets up an instability where a particle can go one way or another, and it eventually chooses and goes towards one or another center of this clumping. And I am told this is actually a common result in this kind of modeling, and that you can get it to work properly by carefully tuning the parameters of your potentials. So I spent several days trying to do that, and I was actually not successful at it. Doesn't mean it can't be successful or shouldn't be, and maybe that is the right way to do this, but I decided to try a different approach, and that's actually good because it gives me an excuse to show you another feature of Tissue Forge. So, or just to go back for a second and reiterate here, I have a potential, and it's being applied to two particle types. The other way that Tissue Forge lets you do this is to apply a potential not to two particle types, so doing it at a global level, but to apply it to two individual specific particles. So you're doing it at a local level. So here in the green box, slightly different statement than before. Now I have, again, a potential, attractive one this time, but I'm applying it to two specific particles. So what's going on here overall is I've iterated over all the particles. For each one, I've found its nearest neighbors. And then for each neighbor, I'm creating a bond between that particle and that neighbor. And so Tissue Forge will render these bonds. If I didn't say so, they're called bonds when they're done on the local basis between individual particles. Tissue Forge will render them as little green line segments, so you can actually see which particles are interacting with which other particles, and it's hard to see them in here. But if I hide the blue particles, you can now see this network of bonds that is created by this code. Okay, so this one right here is to remind me to say, because I keep forgetting to when I was practicing, that this does solve that problem. I don't have a video of it because it would be really boring, because nothing happens. You're already equilibrated, you add the bonds, and you're stable, so the cells just sit there. Okay, so now we could try the same trick that we did before and apply an external force, again, pulling downward toward the vegetal pole, and again, applying it only to the yellow particles. And so what happens is a nice stretching out. You now have a coherent material, a coherent tissue that is being stretched, and that's what we want, and that is a step towards Epiboly. So I should say that I may regret doing it this way. There's actually a little debate in the lab over what is the best way to do this. Is it with bonds or without bonds? And doing it with bonds does make this a more complex situation, because now the neighbor relationships between all the particles are they're fixed in place, and the particles can't rearrange. And cell rearrangement is really important because this tissue is undergoing enormous distortion as you pull it around over a sphere. And so particle or cell rearrangement is necessary in order to accommodate that. So what I'm going to have to do is implement some sort of algorithm to stochastically make and break these bonds, allowing them the freedom to rearrange. Okay, so let me show you one last video. And this is exactly the same as the one I showed you before, except that I let it run a little longer. But also, TissueForge lets you control the camera position and angle, and you're going to see the whole embryo flip over. That's not the embryo doing it. That's me moving the camera down to the vegetal pole so that you could view the whole thing from that vantage point. So same thing. And it's very dramatic and very satisfying, but at the same time, it's also showing some features that are clearly not the way a normal embryo looks. This is not, looks like it's not, this is not Zebrafish Epiboly yet. So I have a ways to go, and but this is where I am today. So I hope this has given you some flavor of what TissueForge is and what it's like to build a model in it and where I'm headed with this. So as for year 2, which would be my first full year in the Institute, I plan to continue working to capture the most characteristic features of Zebrafish Epiboly, the most immediate one being to implement that bond making and breaking algorithm as I just described, but other things will also come up, hence the ... And then to use the model to explore the interplay of candidate mechanisms. So for example, the vegetal microtubule pulling versus the circumferential actin ring constriction and how they interplay with each other and so forth. And then also to work with other embryo labs studying Epiboly to incorporate their latest experiments and data and get a flow going between model and experiment. So thank you for your attention. And thank you to TJ and James for all their help. And also to Aishwarya, if you're in the audience, I hope I'm pronouncing your name right, because I stole a diagram from your talk, something I happened to have screenshotted several months ago from a video in the embryo archive of a talk that was given before I even started here. So if you're in the audience, thank you for contributing a diagram to my talk. So check out TissueForge, and that's it.
Hi,
So
Sharon. This is Mary Mullins. That was really cool. I really, really love it.
Thank you.
That's such a fantastic model. So in the last simulation that you showed us, did that incorporate the breaking of the bonds and rearrange?
No, I haven't done that yet.
Okay, but still, I thought it was a pretty good model. I mean, I'm wondering if the leading edge EVL kind of rearranged the way they, the way they rearranged in the simulation, actually.
So actually, they're not really rearranging. I mean, what they're really doing is crumpling up. So in this configuration here, there's bonds between the yellow particles too, and so it's a nice ring, right? If you ignored all the blue particles, you would have a nice circle, right? Mm-hmm. So by the time it gets to the end, what happens is, you see how it's just folding up. If I were to go here and make all the, again, hide all the particles, and what you would see is that it's still a ring from one yellow to the next, to the next, to the next, to the next. It's just all squished into one area. So what really needs to happen as this ring is getting smaller is to figure out, I mean, in nature, obviously, those cells that are on the margin aren't fixed to be at the margin. That population has got to get smaller. Some particles, or some cells rather, need to leave the margin. I'm sure that as we get smaller, it doesn't maintain the same number of cells. I know that they get squished and elongated a little bit, so maybe it doesn't get reduced proportional to the amount that the circumference is being reduced, but surely some cells are leaving the leading edge. So what should be happening is that I remove them from that ring and they become blue particles, so that you should still just have a nice simple circle of yellow ones here. And but that is, again, part of the thing I have to do about enabling them to rearrange.
Yeah, there's a tight junction between the leading edge EVL cell and the yolk membrane. And I hadn't really thought about it until right now that
That's right.
that has to be removed for this rearrangement to occur. And how that's done, I mean, that's really an interesting question in itself.
It is.
Totally process.
Sorry, go ahead.
Yeah,
No, go ahead.
I'm done.
Oh, okay. Yeah, it is, and it's actually part of in a way, a simpler, more generic question, which is that the same is true within any epithelium. So all of these epithelial, well, not these yet, since it's such a simple model, but in the real embryo, all the epithelial cells have those tight junctions between them as well, right?
Yes.
And so it's a real question. How do cells in an epithelium manage to rearrange without breaking their epithelial function, which involves being a barrier, right? And they are able to do it. So yeah, it's just kind of part of that more generic problem. I kind of think of because of those junctions to the yolk cell, I sort of think of the yolk cell as one more cell in the epithelium. It just happens to be giant.
That's true. That's true. Yeah, we should definitely talk more.
Okay.
Fantastic.
For sure.
Thank you, Sharon. Are other questions for Sharon? Well, thank you very much for the presentation and the cool videos and all the work on Tissue Forge. So we do have time for some breakout rooms. In fact, one of those is going to be if you want to continue to chat with the speaker. Sharon, if you have other questions or want to talk more about modeling in general with Sharon. And then we also have a number of others available. So I'm just going to open those up at this point. And you guys can choose which one you prefer to go into. We've got one that I think is more related to Thrust 4 with computation integration across the undergraduate curriculum. And we have one for each of the biology thrusts and one for students only if you want to just chat among the students, but students are welcome, of course, to join any of these breakout sessions. So I'll keep the meeting open and monitor things as long as you guys want to discuss. So I'm going to go ahead and open those up and let you self-select.